Hello everyone, I hope you brought your model kit today and you're ready to have some fun learning about three-dimensional organic molecules. So last class, we started building different molecules and we just introduced the idea that we can use different ways of visualizing and drawing three-dimensional structures. We started with the dot line wedge diagram on the left-hand side. And I would like you to go ahead and build that while we're getting started. So that is this structure here. 2 carbon atoms, each has 3 hydrogens. That's what we're going to be working with today. We already know how to interpret dot line wedge diagrams, but we're now going to be moving into the Newman projection. Hands up, who is already familiar with interpreting Newman projections? Okay, just a couple hands, not very many. So that means it's new for most of you, which is great. We're going to build some molecules and visualize them today. Just as a reminder, out back of the room today, we have some people from academic advising. If you have any questions, you're welcome to stop by on your way out. So we know this method. This is good for simple molecules. It's not my favorite. I find it not the best. But we can definitely use the Newman projection to communicate three-dimensional shape and, most importantly, conformations. And we're going to be defining that as we go along today. First, to get started, we're going to talk about how to interpret these structures. So we're going to follow these instructions as a class. So we want to assemble a ball and stick model of ethane. And this is what we're going to start with. So pull out 2 of these, and remember that these ones come from your sp3 hybridized little prongs. You push them together and you want to push and pull until you hear a click. And then take 2 of them and put them together. This is the molecule that we're going to be building today. As per this picture here, rather than, the camera is my eyeball here, rather than looking straight down, we're going to be turning on its side and looking down the carbon-carbon axes. So when we draw this, when we're drawing a Newman projection, so hold up your ethane molecule if you have it. Okay, so we see the 2 carbons, the 3 hydrogens on each carbon, and then we look down that carbon-carbon bond. So you can kind of hold it up to your eye. When you looked straight down that carbon-carbon bond, you can't actually see the second carbon atom behind the first one. But that's okay. We know there's a carbon-carbon bond there, and we're looking at what's attached to those carbon atoms. The front carbon that's closest to your eyeball is going to be a dot. The back carbon that you can't really see is going to be a big circle. So when we draw our Newman projection, draw alongside me in your book. The front dot is that carbon that's closest to your eyeball. The back one is the big circle. So go ahead and draw that. Then we want to show which way the bonds are pointing. So I'm going to take my model here and I'm going to line it up to the picture that I see in my workbook. In my workbook, I can see the front carbon here is attached to a hydrogen and it's pointing straight down. So I'm going to hold this up to my eyeball or down on the camera here. This front carbon has a hydrogen that's pointing straight down. If I orient the front carbon to hydrogen bond like this, that means I have a carbon-hydrogen bond pointing up to the left and another carbon-hydrogen bond pointing up to the right. So we can see that front carbon is different than the back carbon. So I have that carbon-hydrogen bond pointing down from the front carbon and up to the left and up to the right. That takes care of this front carbon here. But then I need to show how the back carbon is. And based on the picture that we see in your workbook, the back carbon has a carbon to hydrogen bond pointing straight up. So we're going to draw that one in first. The back carbon is the big circle, and that carbon-hydrogen bond is pointing straight up. We communicate that it's on the back carbon because we don't draw that carbon-hydrogen bond right from the dot. We draw it from the bigger circle to show that it's the back carbon. And then we have a carbon-hydrogen bond down to the left and down to the right. So we have now drawn the Newman projection that you see in your workbook. Now this is really handy because carbon-carbon single bonds can rotate. And you can go ahead and do that, and you can see that the view changes as we rotate the back or the front carbon. Go ahead and rotate that carbon-carbon single bond. This is the cool thing about carbon-carbon single bonds. They can rotate. Double ones, those pi bonds break when we rotate them. But here we certainly can rotate. I haven't broken any bonds. I haven't made any new bonds while I rotate it. So it's the same molecule, but it's a different conformation. This is one conformation, this is a different conformation, and so on. So we're talking about conformations, and Newman projections help us to visualize and differentiate between these different conformations. So here we have our definition of a conformation. These are transient. So it doesn't mean that this molecule stays like this forever or like this forever, but they can be rotating all the time. So they're transient, they're short-lived, they could be rotating. They're spatial arrangements, so just pointing in different directions, but it's the same molecule. This is not an isomer, so make a really big star in your notes. We're not making different isomers, we're just making different conformations of exactly the same molecule. We do that by rotating around this carbon-carbon single bond, or a carbon-oxygen single bond, or whatever it happens to be, because those single bonds can rotate. They're not pi bonds. So to get us started today, I have a somewhat challenging problem. It's going to be easier if you take that ethane molecule, turn it into a di- or trichloroethane. So I suggest taking some colored balls, leaving the prongs empty if they're hydrogens, but adding a little ball to indicate where your chlorine atoms are. So see if you can build the molecule with the wedge-hatched diagram. It has 3 chlorine atoms. 1, 2, 3. Go ahead and build that molecule. Line it up exactly as you see it in that diagram, and then identify A, B, C, D, which of these interprets and shows you the Newman projection of this exact conformation. Chat with the person beside you and submit your answer. Try looking from both angles, and remember that these little balls have a thin end and a thick end, depending on if you're putting it on a thick prong or a thin one. And I'll give you 10 more seconds. So this is a reminder, make sure you're bringing your model kit to class until the end of the term. Today's class is fully reliant on having that model kit. So it's definitely in your best interest to use it If you don't have yours with you today, I encourage you to go home and build these molecules while it's still fresh in your mind about what we talked about. You can greatly reduce your memorization pain by building the molecule and having it make sense. And 3, 2, and 1. Okay, most people going for D, and that is correct. We had a number of options or votes for B, so let's chat about that. Okay, so I have built this molecule as well. I have the carbon to chlorine bond on the plane of my page, the carbon chlorine coming towards me out of my page, that's my wedge. On the right-hand side, I have the carbon chlorine bond in the plane of my page pointing straight up, which means I have a carbon hydrogen pointing towards me and a carbon hydrogen pointing, or a hydrogen pointing away from me. So then I want to look down this carbon-carbon bond, or look down from the other direction and see which one exactly matches these Newman projections. I don't want to rotate this carbon-carbon bond because that would change the conformation. And this question is asking us to find the exact conformation. So I'm just going to jump to the correct answer, and then we're going to talk about how we can rule out the other ones. In option D, you can see the front carbon has 2 chlorine bonds, one pointing straight down. So I'm going to cover these up. One pointing straight down, one pointing up to the right, and a hydrogen up to the left. The back carbon chlorine is pointing exactly straight up, right between the front chlorine and hydrogen atom. We can see the back carbon has a hydrogen down to the left and down to the right. So this model, I'm going to almost set it down, exactly matches what we see in D. What's wrong with A? Does someone want to shout it out? Why is A incorrect? Okay, you've probably all identified that it's the front carbon that has 3 carbon chlorine bonds. That means that these 2 molecules are not conformations because we couldn't just rotate this carbon chlorine bond to produce A. To produce A, we actually have to break a carbon chlorine bond, form a new carbon chlorine bond, which tells us we have a new molecule. I still have the same total number of chlorines, carbons, and hydrogens, so that means this is an isomer. It's a constitutional isomer because it has the same molecular formula, but a different connectivity. This chlorine is now on the carbon 1 rather than carbon 2. So A and our molecule of interest are constitutional isomers. Same molecular formula, different connectivity. Okay, if we look at B, how is B related to our molecule of interest? We're going to do hands up. Is it an isomer or is it a conformation? Hands up for isomer. Hands up for conformer. That's correct. So it's the same connectivity. It's based off of the same isomer, but to get B, I'm just going to go back to my structure here. What did we have here? We had up and towards us and straight up. This is our molecule of interest. To get B, we look down the carbon-chlorine bond that has 2 chlorines on the first carbon and 1 chlorine on the back. Let me see if I can match it up properly. There we go. The front carbon, I've aligned with what we see in the Newman projection for B, but the chlorine is in the wrong spot. In the Newman projection for B, it's showing the back chlorine. We have to twist that carbon-carbon bond so that all 3 of these chlorines are in kind of the same proximity. They're kind of close to each other. The back carbon-chlorine bond is falling right between these ones. We just rotated, so that means it's a different conformation. So these are conformers. Okay, what about our molecule and option C? Who thinks they are conformers? Isomers. Not even related. And not even related is the correct answer. C only has 2 chlorine atoms. Our molecule of interest has 3. That means they have a different molecular formula. They're not isomers. And they're not the same, and they're not conformers. And that's how we got to D. So we spent some time on this question because we need to be confident going back and forth between different structures and identifying what's the same, what's a conformation, what's an isomer, and what is even not related. And let's make sure that is very clear. Okay, excellent. Let's keep jumping along here now. Different conformations have different stability and energy levels. There are 2 big differences that we're going to distinguish between here. The first, so I'm going to take my ethane again, and you can as well. You can take those chlorine balls off because we're going back to our regular ethane. First conformation that I'm going to make is called eclipsed. So when you think about a lunar or solar eclipse, I'm not an astronomer, so it's when the moon blocks out the sun, right? Or the earth blocks out something. But it's when they're exactly overlaid. They're eclipsing one another. So in an eclipsed conformation, go ahead and follow along with me. Look down the carbon-carbon bond, but align the rotation so that the carbon-hydrogen bonds are exactly overlaying in physical space with the front carbon-hydrogen bonds. So if I hold it really carefully, you can hardly even tell the molecular formula. C2H6, it kind of just looks like CH3 because you can't even see the back ones. These bonds are eclipsed with the back bonds. These back bonds are eclipsed with the front bonds. This conformation is a little less stable, which means it's higher in energy. Why? Because these 2 carbon-hydrogen bonds and these 2 carbon-hydrogen bonds, or whatever those substituents may be, are kind of in each other's space. And atoms like to have as much space as possible. Remember Vesper theory? They try to get as far away from one another as possible. That's the problem here. So right now they're eclipsed, and these are just in each other's space a little bit. If we rotate that carbon-carbon bond so that the front carbon-hydrogen bond does not exactly overlap, now you can see all of the bonds. This one is like, how many degrees is that? 160 degrees different than the orientation of this one. You can see that there's a little bit of space between all of these carbon and hydrogen. So hold this up to your eyes. Try rotating. Look, find the eclipsed conformation when you can look down them and they all align. Rotate 60 degrees and find the staggered conformation. So staggered, you can think about how bricks are laid or backsplash tiles or whatever. This is the staggered. Staggered is more stable. It has lower energy because each of these substituents, especially matters when they're bigger than hydrogen, have their own space. Again, when you're looking down that carbon-carbon bond. We're going to take our ethane, and now I'm going to add 2 methyl groups. 1 methyl group to the front and 1 methyl group to the back, which means now I have actually butane, carbon 1, 2, 3, and 4. But I'm going to look down that carbon-carbon bond to make my Newman projection. So you go ahead and build this molecule as well. And we're going to rotate and make different conformations and see how these large substituents start close to one another and get farther away from one another. You can see in this conformation, these 2 bulky substituents up here are in each other's space. If we rotated that carbon-carbon bond, we could get these bulky substituents farther away from one another. Here, we have some steric repulsion happening. This likes to have its own space, this likes to have its own space, and they kind of repel each other. So that's where the word repulsion comes from. Sterics means like getting in each other's space. So due to this conformation, it is highest energy, least stable when we look down this carbon-carbon bond. If we rotate them far apart from one another, it's much more stable. They have more space. We're going to do this step by step, and I'm actually going to swap out my two methyl groups for red balls, just so that it's a little clearer on the document camera. So you're welcome to keep using the methyl groups or switch to the red balls. Now, when we're talking about rotating, we're referring to something called the dihedral angle right here, which means you're talking about intersecting planes. So I have two pieces of paper with me here today. Green is my plane 1, yellow is my plane 2. If I hold my papers like this, what is the dihedral angle? Go ahead. 90 degrees, that's right. We can see these are orthogonal to one another. If we look straight down these two planes, they're 90 degrees apart. If they're flying flush with each other, I'm going to call that 0 degrees apart. If they're halfway to 90, there's our 45, our 90. What's this angle? Go ahead and shout it out. 180, that's right. They're flat from one another. Then here is it 90 versus 180 plus 90, whatever. But you can see we can measure these angles. We already know how to do bond angles, right? You just check the difference. Now, rather than just two lines and looking at the angle for two lines, we're looking at the angle of intersecting planes. And so if you want to look at this on the document camera, here is our 90-degree angle, our dihedral angle. Here we could say it's like 45 degrees. Here it would be 180 degrees. So we're looking at the intersection of these planes. So when I talk about a dihedral angle, I'm talking about substituent in the front, carbon in the front to carbon in the back. So I'm talking about red ball to carbon. I'm going to line up my plane there, all the way to the carbon in the back. So I've made a plane with my substituent to carbon 1 to carbon 2. That's what my plane is. Then I'm looking at another intersecting plane. This is my back substituent, carbon 2 to carbon 1. So it's like this. So I could, they start right next to each other, and then we can rotate and rotate. Now you can see they're like 180 degrees apart versus right side by side. Okay? So we're starting flush with each other, and we're going to go to a dihedral angle of 180 and then all the way around to 360. That's a dihedral angle. Okay, so in the picture, top left, we have our two methyl groups eclipsed with one another. We're going to take that back carbon and rotate it 60 degrees, and now we have a staggered conformation. And our two interesting groups are now 60 degrees apart because we rotated it 60 degrees. And of course, we rotated that whole angle. Well, we can rotate another 60 degrees. We're going to keep the front carbon in the same arrangement. We're going to rotate 60 more degrees. Now we're at another eclipsed conformation. And if you're looking at it this way, look straight down that carbon-carbon bond and line up all of those bonds. If we rotate 60 more degrees, we're now at a dihedral angle of 180 degrees. We've gone from this all the way to this. And now we can see the chlorine atoms are as far apart from one another as possible. We are in a staggered conformation, And this is the most stable staggered conformation because these two big substituents are as far apart from one another as physically possible. So we've gone 180. Okay, so we can actually plot the energy level of these different conformations, and you can predict the relative energy level of different conformations of unique molecules. So we are going to keep the front carbon and its methyl group in the same spot. So that front carbon has its methyl group pointing down, and the back carbon has its methyl group pointing up. Is this one staggered or eclipsed? Hands up for staggered. Excellent. It is staggered for sure. I'm going to take that back carbon and rotate it 60 degrees to an eclipsed conformation. I'm now at position number 2. Look at how the energy went up to get up to position number 2 because we now have an eclipsed situation happening. Well, we then rotate that back carbon another 60 degrees. So you go ahead and do that. Hands up, is this number 3? Is it staggered or eclipsed? Hands up for eclipsed. Hands up for staggered. Yes, it is staggered. We can see that these two substituents are closer together now than when they were when we started at position number 1. In position number 1, those groups were as far away from one another as possible. That was the most stable staggered position. Now, they're still close to one another, but they're still in a staggered position. This position is called gauche. If we have a staggered, but the groups are still somewhat close to each other, it's called gauche. That's in contrast to anti, when those groups are as far apart from one another as possible in a staggered conformation. Okay, and then we're going to take that back carbon and rotate it 60 more degrees. And now we can see these two substituents in molecule number 4, conformation number 4, are eclipsed. Look at how high this energy level is. It's the highest energy level of all the conformations of this molecule. It's eclipsed, which is higher energy than staggered, and it's the worst option of eclipsed because the two biggest substituents are directly overlaying one another. Well, we can keep going, rotate another 60 degrees, and we get to molecule number 5, or conformation number 5. This is another gauche position. So number 3 and 5 are both called gauche. They're both staggered. The substituents are kind of close to each other. We rotate 60 more degrees, and we're back to another eclipsed position. But see how conformation number 6 is lower in energy than conformation number 4. It's eclipsed, but the biggest groups are eclipsing hydrogens. So your red balls are overlaying with hydrogens now. We rotate 60 more degrees, and we're back to where we began with conformation number 1. Staggered, so it's lower energy, and the two biggest groups are as far away from one another as possible, so it's back to our anti position. All of these top conformations are eclipsed. All of these bottom conformations are staggered. So based on this pattern, you can predict the relative energy of different conformations. Again, you need to know this, but don't memorize it. Build the molecule and convince yourself of this type of pattern. Okay, so I would like you to work with the person beside you. Which of the following statements is correct? We have different conformations of different molecules, or the same molecule, which one is incorrect? Not correct. And 10 more seconds. And 3, 2, and 1. Okay, 3/4 went for statement C. I agree. That means A is correct. Z is more stable than X. Why? Well, they're staggered versus eclipsed. That's the simplest comparison. W is more stable than X. That is also the case because it's staggered versus eclipsed. Z is more stable than W. This one's a little bit trickier because they're both staggered, so they're both more stable than eclipsed. But then we have to pay attention to the different options. Z is the anti, W is the gauche. Those two ethyl and methyl substituents are still in closer proximity in W compared to Z. So well done. So we need to understand isomers, but we also need to understand conformations, different rotations of molecules in space, which ones could exist, which ones do exist. We're going to come back to conformations, but before we get there, we need a little conversation about cycloalkanes. So we are going to build and compare some cycloalkanes now. So far, we've been working with acyclic hydrocarbons. That means linear or branched. But now we're going to take, I'm going to start with a big one. You don't have to build this one here. We're going to take our carbon chain, our acyclic hydrocarbon. We're going to take one end of it and the other end of it, wiggle it together, and bring those two ends together to make a cycloalkane. When we did that, I needed to put my hand on one of these carbon-hydrogen bonds in my acyclic molecule and one of the carbon-hydrogen bonds in my other end and bring those together. And those prongs are now no longer carbon-hydrogen bonds. They're used to make up a carbon-carbon bond, which means the ratio of carbon to hydrogen atoms in a cyclic compound is different than the ratio in an acyclic compound. Do you remember acyclic compounds had carbon and hydrogen? It had twice the number of hydrogens, but then we needed to add 2 extra hydrogens, one on each end to fill out those filled octets. If we're talking about a cycloalkane that has 1 ring, those 2 extra hydrogens on the end need to be removed so that those electrons can be used to make a new carbon-to-carbon bond. So, cycloalkanes have the carbon-hydrogen ratio of 1 to 2. So looking at the molecular formula, sometimes you can predict it has a cyclic compound. I mean, it could also be a double bond, but that's a conversation for next week. So let's start with our cyclopropane. We have different types of cyclic molecules, and we're going to work through all of these different ones. So we're going to start here with cyclopropane. So you're going to take 3 of your carbon tetrahedral pieces, or take that ethane piece, grab another one, start with a propane. This would be CH3, CH2, CH3. But to make it a cyclic compound, we're going to take this hydrogen and this hydrogen, remove them, and really tightly put these together. Now, you may or may not want to copy me on this because you can see that I'm damaging my model kit right now. See how I'm bending that prong? It actually turns white and damages the plastic. So you might not want to do this. See how that's a terrible bond angle? Normally, they line up nice and straight between two carbon atoms. This is a highly strained structure. The overlap of these sp3 orbitals is pretty bad. So this is not very stable. So this one we can say is highly strained. And you can see that just because when you try to do it, it's bending like crazy and damaging your model kit. That said, the carbon-carbon-carbon bond angle here is 60 degrees. In a normal methane group, CH3, that bond angle is 109.5. 60 is a whole lot smaller than 109.5. So this cyclopropane, not very stable. In addition to this really sucky carbon-carbon bond, if you look down that carbon-carbon bond like a Newman projection, do you see how this carbon hydrogen exactly overlaps with the back carbon hydrogen? And this one overlaps as well. These bonds are eclipsed, and we know that that is less stable as well when they're eclipsed rather than staggered. So for all those reasons, not awesome for stability. So it's quite high energy. So let's move up to our cyclobutane. This bond is ready to pop. There we go. We'll help it out. I'm going to add another carbon hydrogen. Again, if this was acyclic, we would have those two extra hydrogens at the end, but I'm going to remove those two hydrogens and make my cyclobutane. Now this one, you could flatten it out, look down the carbon-carbon bond, and see that these, whoops, carbon-carbon bonds are, it really strained it, are eclipsed. But this one can actually behave like a butterfly. So if you have your cyclobutane, try making it fly a little bit like a butterfly. Look what happens to the carbon-carbon bond. If I squish this down, I'm going to swap out the carbon that I just broke. Poor prong got too strained. I'm going to damage another one now. Okay, you can still see it's slightly strained here. The bond angles from carbon to carbon are now 90 degrees rather than 109.5. So again, it's not ideal, but it's a whole lot better than cyclopropane. If I squish this down and I look down a carbon-carbon bond, it looks eclipsed. But this butterfly can fly like this. If you make it fly and then look down the carbon-carbon bonds, look, I made them slightly staggered. So the molecule is actually slightly staggered because it's not perfectly planar. It's a butterfly. And so it's partly staggered. So the butterfly is actually called puckered. So it's like kind of like melted plastic bubbles a little bit. It's pushed up a little bit. Still some strain in those bond angles, slightly staggered though on the carbon hydrogen. Okay. Cyclopropane isn't very common. Cyclobutane is more common. Cyclopentane is even more stable and even more common. So here we have our cyclopentane. We can see the ratio of carbon to hydrogen is 1 to 2. Every single carbon atom has exactly 2 hydrogens attached to it. Now this one also turns into a butterfly. It's not perfectly flat. If it was, all of those carbon-hydrogen bonds would be eclipsed. So it actually turns into a butterfly as well. When we do that butterfly motion, or puckered, as it's officially called, we can look down these carbon-carbon bonds and see that these are quite nicely staggered now. If I look down this one is eclipsed. Not all of them are perfect. But if you look down the next one, that's beautifully staggered. And the next one is beautifully staggered as well. So hopefully you have that cyclopentane in front of you. Turn it into a butterfly or a puckered. Look down those carbon-carbon bonds and convince yourself that this one has minimal strain and mostly staggered. And we know that molecules move too, right? So it probably is actually working like a butterfly. Okay, and now we move to our final option. If you haven't built any molecules, now's your time to engage and make a cyclohexane, because this is the one we're going to be using for the next 2 classes. Cyclohexane is the most common cycloalkane that we have. You can see the bond angles here when you make it are 109.5. Exactly what we would expect them to be in an sp3 hybridized system. Now, this one can definitely move. You could do like a butterfly. We're going to talk about how to make these different conformations. But when you make it, you can really make it move. And it does. It has different conformations when we make this cyclohexane. It has 2 main conformations, and we're going to learn how to make those right now. The first one is the boat. So this is where you want to make sure that all of your tetrahedral carbons that you built have those pieces snapped together. If they're not snapped together, your molecule's about to fall apart on you. So make sure those clicked in. You've made your cyclohexane. When we have a cyclic molecule, start counting the carbons at whatever substituent is most interesting. Here they're all hydrogen, so I'm going to start wherever I want. 1, 2, 3, 4. Put your hands on carbon 1 and 4. You can make it jiggle all around. But take your 2 hands and bring them up together like this. And if you don't have your cyclohexane, bring it next class, because this stuff will make a lot more sense when you have it. This here, rather than our hands down or somewhere else, when we bring both hands up on carbon 1 and 4, this is called a boat. So in my boat, there is the bottom of my boat. It's like a rowboat. Here's the front of the boat, the back of the boat. This is where you sit in the boat. This is where you paddle. This is my boat. Okay? Look at these 2 carbons that are pointing towards each other on carbon 1 and carbon 4, where my hands were, where I brought this up. These 2 have some flagpole interaction. These 2 substituents are definitely getting in each other's space. This conformation is not the most stable conformation because of this flagpole interaction, those substituents that are really close to each other. As well, let's look at the staggered and eclipsed situation with the hydrogens. So I'm just going to start at carbon 1 and look towards carbon 2. Try to line this up. These are all staggered. The next one, those are eclipsed. Next one, staggered, staggered, eclipsed. Some of the carbon-hydrogen bonds are eclipsed in this row, row, row your boat structure. What's better? So this one actually exists, like less than 1% of cycloalkanes exist in this position. 99.9 exist in a conformation that's called the chair, where all the carbon, hydrogen, or carbon whatever substituents are in staggered positions. So take your hands on carbon 1 and 4. Keep your right hand up at the front of the boat. Take your left hand and flip this one down. When you have the perfect chair conformation, you can see the back of the chair, the bum of the chair, and your footrest. When you have a perfect chair conformation, set it on your desk, and it will sit on exactly 3 prongs. It has exactly 3 prongs pointing down, exactly 3 prongs pointing up. And this is your chair conformation. In your notes, you can see this is the back of the chair, the footrest of the chair, the bum seat of the chair, and here is you relaxing on the chair. We have different positions in this chair conformation. The straight up ones versus the ones that poke out have different names, and they help you to figure out the relative stability or the energy of that conformation. When we come back next week, please bring your model kit. Come with a cyclohexane. We're going to learn how to do flip-flops with cyclohexanes and see different conformations that you can make. Have a great weekend. I will see you on Monday with your model kit.